Yeah. So we shall continue from where we left off in the last class, where we wrote down the expression for the virial coefficient B2, which is equal to minus 2 pi 0 to infinity e to the power minus beta two-body potential UR minus 1 R square dr. And now the rest of the discussion shall mainly focus on the properties of B2 and how it, and depending upon whether it's positive and negative, you're going to have the modified gas equation. By modified gas equation, I mean corrections to the ideal gas equation, because in general, the virial equation can be written as P by KBT into N being N by V. So if you didn't have these extra terms, you would have the ideal gas equation, PV equal to nu RT, nu being the number of moles. Whereas if there were interactions, then the gas equation would have corrections. There would be terms, these would be the virial coefficients which add corrections, where this is the second virial coefficient, and this is the third virial coefficient. And depending upon whether B2 is positive or negative, the additional term, so this will be a positive quantity, the N is capital N by V, N being the number of particles, but this is a positive quantity, but B2 being positive or negative will decide whether the gas, because of the interactions, will have the pressure of the interacting gas will be less than or higher than the ideal gas equation. I mean, ideal gas pressure at the same temperature and volume and so on and so forth. Right? So you're keeping the volume constant, the temperature constant, and that temperature, there would be a certain value of the pressure due to an ideal gas, and depending upon B2 is positive or negative, the resultant pressure will be higher than the ideal gas pressure or lower than the ideal gas pressure. Right? So that's what B2 is going to do. And the expression of B2 is this. And this has note the temperature. So the value of B2 is going to change. If you change the temperature, if you have a different potential, then the value of B2 is going to change. And the ratio of the interaction potential and the value of the temperature suitably integrated over R, where we are considering only two body potentials, is going to decide the behavior of the gas at different temperatures, right? So with this, let's go in more detail into a discussion of the behavior of B2 as a function of temperature, as a function of depth of the potential, and so on and so forth. So B2, what I have done here is written the previous expression, minus 2 pi 0 to infinity, e to the power beta, beta being inverse KBT, the pair potential minus 1 R squared dr. If you have any confusions about where this comes, please refer to the previous lecture. And that has been broken down into two parts. So one is an integral from 0 to R0 and R0 to infinity. Now R0, though I have used the term R0, I should remind you it is the diameter of the particle. And why is it the diameter of the particle? Just to remind you, so this was R0. So if two particles are touching each other, that's the distance of, that's the diameter, because half of the R0 is the radius. And when two particles start touching each other, then they face an infinite repulsion because charge clouds are overlapping. And beyond R0, right? So R0 is the diameter when two particles are touching, and if the radius of two between the centers, because it means less than R0, then there is a strong repulsion. This is the Lennard-Jones potential, which can be integrated. I mean, you can integrate Newton's equation of motion, whereas it's more difficult to work with infinite potentials. depending upon, yeah. So let me not make that it's more difficult or not. I mean, I was talking with the computational physics course, but yes, I mean, yeah. So the R0 is the diameter. With that perspective, so the integral is from 0 to the diameter and diameter to infinity, and the nature of the potential changes. Uh, so the nature of the potential is strongly repulsive between 0 and R0, and is attractive between R0 and infinity. Hence, we have broken it up into two parts, where I have reminded you that sigma or R0, I mean, sigma is when the way you write the Leonard-Jones form of the potential equal to R0 is the diameter of the potential. Just to, before we go ahead, let's get an idea of the dimensions of B2. So I want to remind you that in the virial equation, the left-hand side of the equation has P by kBt. Now, pressure is force by area and has the same dimensions as energy by volume. Now, kBt is a unit of energy and has dimensions of energy. So, the P by kBt has dimensions of E by V by E, dimensions of E. So, these square brackets denote the dimensions of this quantity. And so P by kBt has dimensions, as you see, of 1 by V. And on the right hand side of the equation, you have N by V, of course. And furthermore, you have the virial coefficient. Somewhere I've written, yeah, virial coefficient into n square v square, right? So if you equate that, then you can easily see, because dimensions of P by kBt is 1 by volumes. Similarly, the first term is n by v. It says dimensions of 1 by volume. And this will have dimensions of, so sorry, I should have a square bracket here, suggesting that I'm really looking at the dimensions. So 1 by V dimensions has the same as B2 by V square, which implies that B2 has dimensions of volume. Okay. Now taking the potential, so evaluating these integrals to get an idea of how these integrals are. So 0 to infinity, so there's this minus 2 pi sitting here. So sorry, so this term 0 to r, we are doing 0 to r e to the power. So between 0 to r, the potential is nearly infinity, right? I mean, if you take Leonard-Jones, then it's sharply increasing towards infinity as 1 upon r to the power 12. If you take the simplified version, then it is really infinity uh, for all distances less than r0. So in that case, you have e to the power minus plus infinity, because the potential goes to infinity and you have a minus sign here. So basically infinity by kBt minus 1 r squared dr. Now this thing is 1 by e to the power infinity, and that's 0. So all that contributes, and you have a minus sign here and a minus sign here. So when you integrate, what you get is 2 pi r0 whole cube by 3, right? So since R0 is the diameter, this is always going to be a positive quantity. Here we have assumed that the potential is infinity for all distances between two particles less than R0, right? So it's a positive quantity. So this is going to be always positive. However, this term is typically negative. And how do we see that? So just to see R0 to infinity, and you have your minus 2 pi sitting here, R0 to infinity. Now this U0, this was an attractive potential. So it comes with a negative sign. So when you So when you have this e to the power minus beta and the potential comes with a negative sign, you get a positive sign. I've explicitly written down u0 by r to the power 6, but it could be any other function as well, into r square dr. Now, this term, e to the power 0 is 1. And any positive quantity, beta u0 r to the power 6, any positive quantity, because u0 is positive, the potential was negative, but u0 is positive. This is going to be some quantity greater than 1. It might be small. It might be small if kBt is very high, right? Because it's u0 by kBt r to the power 6. We're going to explicitly calculate as well. But whatever be, this is going to be greater than 1, even if it be small. As a consequence, this term is always going to give a negative contribution. Now, if kBt is small, for a relatively small value of kBt, a small value of kBt doesn't make sense. Small with respect to what? With respect to u0. So if u0 by kBt is small, which means this quantity is large, right? So you will have a large number here, depends upon r, of course. It is slowly falling as r decreases, but for r equal to, suppose, r0 or whatever, this is a large quantity. This is going to be a large quantity. Hence, it is going to be a large negative value on integrating, right? We are integrating over different values of r, and it is going to dominate over this term. So if kBt is small, B2 is going to be likely negative. However, if temperature is high, then we'll show in the see in the next page that this is nearly going to be equal to 0. Why? Because u0 by kBt is a small quantity. It's a number closer to 0, right? Of course, there's an integral and so on and so forth. But if kBt is high, then this contribution is going to be low, right? And as a consequence, this integral can have relatively small values, right? And in that case, the sum is going to be positive. So what we see here is that at small kBt, the sum of the two terms is, at small kBt, the second term is going to dominate. This is going to be large, and the modulus is going to be large, and it's going to be negative large number. So that is going to dominate over this. Yeah, you have to consider the minus 2 pi as well. So if you consider the minus 2 pi, it will be a large negative number. So the contributions from this is going to be large negative. The contributions from minus 2 pi into this is going to be 2 pi r0 by 3. That is going to dominate, and it's going to be negative. On the other hand, at high kBt, since this term is going to be relatively 0, a small negative number, the sum of this and this terms is going to be positive, right? And and as kBt increases, the contribution of this is going to go down. So basically, the value of B2 is going to gradually increase as you go on increasing kBt. However, there's a third case, and one has to be a bit careful. So this discussion, of course, holds true, but here when we calculated this quantity, we also assumed that basically this is e to the power minus infinity. But practically, atoms are going to be able to overlap to some extent, right? I mean, if the two particles have extremely high kinetic energy, which corresponds to high temperature, or if on average the particles have very high kinetic energy, then to some extent they can overlap. And that's why in the Lennard-Jones potential, you don't have an infinite barrier, but you have a slowly, gradually, I mean, not gradually, sharply increasing function. So the potential is sharply increasing as you decrease R. So in general, if we write the first term as e to the minus a by kbt, and a is a positive large number, right? When kbt becomes very high, when kbt becomes much higher than this, then this is already 0, but it becomes so that the value of kbt becomes comparable to this large number, then this term, so this term was considered 0 when we had calculated the value of the first term to be 2 pi r0 cube by 3. But when the kbt is even higher, what will happen is that this term will also start to contribute. It will be non-zero because kbt is high. This is a very large number. When a by kbt become comparable, this term is going to be 0 at kbt very high, but this is also going to contribute to this. And the effect of this contribution is going to decrease. So at very high kbt, when a is order, the magnitude of a is order of kbt, and a is a large positive number. So this is going to also start contributing. So the first term so the first term will be 2 pi r0 cube by 3, right, which comes from this term. Essentially, there's a minus sign here and a minus sign here, minus 0 to r0. Why minus? Because this minus 2 pi is going to come here. E to the power minus beta a r square dr. So this is going to start to contribute. So in medium temperatures, intermediate temperatures, this is going to be close to 0, and this is progressively going to smaller and smaller negative values. So value of B2 is going to increase, positive and increase. At very small t, it was negative. At intermediate values of kbt, it is going to increase, become positive first of all, which means cross 0, and become positive and keep increasing. But at very high temperatures, when kbt becomes order of a, then again, because of contributions from here, from this term, the B2 is going to gradually decrease. So what I'm showing here is Rife figure 10.4.1, figure Rife 10.4.1, where the value of B2 normalized by R0 cube has been plotted for different values of kbt by U0. Why kbt by U0? Because kbt really matters only. So basically, it's a dimensionless number, and kbt high and kbt low doesn't make any sense unless you compare it with the value of U0, right? High with respect to what? With respect to the intrinsic energy scale of the problem, right? Whatever is the intrinsic energy of interaction, it's with that you have to compare kbt high, kbt low. So hence it is plotted versus kbt by U0. So it shows that for low values of kbt compared to U0, the term, the virial coefficient B2, it's normalized by R0 cube, is negative, but it gradually increases, becomes positive, and note thereafter in region 3. So this was region 1, this was region 1, second is region 2, it is positive and its value is increasing. But then at very high temperatures, when kbt is 50 times u0, right? So then the integral starts to contribute, and you see b2 is gradually decreasing, right? Now that's the functional form. So the straight lines have been plotted by using the Lennard-Jones potential, right? Because unless you have the Lennard-Jones potential, if you take an infinite potential, will basically this will increase and saturate and become flat. It's only if you take the Lennard-Jones potential where you allow the terms to interact so that this term has a possibility to contribute, do you get the slight decrease in B2 at very high temperatures, else you wouldn't get it, else it will just saturate and become flat. So this has been calculated using the Lennard-Jones potential, and also experimental data from using the equation of state. You can measure pressure, you can measure volume, you can measure the corrections. So you can measure at a fixed temperature, you can measure pressure and volume, or uh, you can change the temperature and look at PV curves, right? And from there, you can back calculate B2, and I'll tell you how to back calculate B2 in more detail soon. And when you compare the two, it really matches on top of each other. But there were, of course, two fit parameters here. One of the fit parameters was the diameter, because you don't know a priori what is the diameter of an various gases, and here it was shown for so it fitted well with argon, nitrogen, methane, hydrogen, neon, helium, and you can see that the nature of the curve really matches well, and by fitting you can get the depth of the potential, the interaction depth of the potential, u0, right, which is the energy unit, and u0 by kb, that is so u0 and kb have energy units, so u0 by kb has values of 120k, and by fitting for argon, they found out that R0 is equal to 3.82 angstrom, which is very reasonable. And you see, by using this theory, one can microscopically calculate the value of B2 and also try to fit it, and so on and so forth. So you get this van der Waals equation. Well, we have not reached van der Waals equation, but we'll soon reach. So B2, so writing down, so getting a more close form of B2, and now what we are trying to do is not just compare with experiments, but try to get the van der Waals equation. With that, we are writing B2 as 2 pi, the minus sign has been absorbed, 0 to R0, R squared dr, where we have already used A equal to infinity, so that term is not contributing, minus 2 pi R0 to infinity e to the power minus beta, the potential minus 1 r squared dr. Now, assuming high temperatures, assuming that it's a interacting gas, what we have done is written e to the power minus beta u r, the potential term, as e to the power beta. It was a negative potential, so this minus and the negative potential cancels. U0, the energy unit, R0 upon R to the power 6, right? Where we are using the steep, we are using really the steep, the potential is infinity at, if the distance between two particles is less than R0. And if temperatures are high, so beta is high, U0 by beta is low, then one can write this as 1 plus beta u0. So what we are using, we are keeping the first term and neglecting the other terms, higher order terms of the exponential. And now it is much easier to calculate B2 is 2 pi 0 to R0, which is this term R square dr. And if you integrate it, you will get 2 pi R0 cube by 3. And here, if you substitute beta u0, I've kept it here, 2 pi is sitting here, and all that you have is R0 to infinity. You already had this R square, and r0 to the power 6, r to the power 6, right? And if you integrate that, r0 to infinity, 1 upon r cube, sorry, 1 upon r to the power 4. When you integrate, you will get minus 1 upon r cube, right? And the limits are r0 to infinity, right? So 1 upon infinity is going to give you 0 minus 1 upon r0 cube, but you already had a minus sign here. So from the limits, you get a minus sign, and from the integration, you get a minus sign. So those two cancel, and this minus sign remains. Thereby, you have this minus sign. And on substituting, what you get is, you have r0 cube here and r0 to the power 6. As a consequence, you get 2 pi beta u0 energy unit by 3. This 3 is sitting here, r0 cube. And from this term, you already had 2 pi r0 cube by 3. Remember, r0 is the diameter. In that case, you get a closed form for B2. You're taking your 2 pi r0 cube by 3 common, and you get 1 minus u0 by kBT. See, I mean, u0 and kBT have the same energy units. And this in turn, one can write it, this 2 pi r0 cube by 3, I'm writing it as b dash minus u0 b dash by kBT, right? B dash, we had already checked, had units of volume. And here again, we are getting units of volume. B dash equal to 2 pi r0 by 3. So finally, we are ready to put it. So we have an expression for B2 now in terms of the microscopic energy of interaction, and 2 pi r0 whole cube by 3 is B dash. And that's exactly what we put in the virial equation of state. In that, we write P by kBT equal to N, which is the ideal gas term, into, now we have an expression for B2. So B dash minus B dash U0 by kBT. Remember, this has the same units, into N square, where N square is, well, N is capital N, number of particles in the unit volume, which in turn can be written as, well, all that we are doing is taking the kBT on this side, N kBT, sorry, no N, kBT B dash into B dash U0 and kBT, and this kBT cancels, into N square, right? Now, all that we are doing is taking this B dash U0 N square term to the right hand side. So B dash U0 N square to the right hand side of the equation, plus P. And what remains on the left hand side is N kBT 1 plus. So what we have done is taken kBT out. So this term has kBT and this term has kBT. As a consequence, we have taken N kBT out of the brackets. We have taken it common. So this gives 1, and this didn't have N. So when you take N kBT out, you have to divide, what are we doing? There was an N square here. Yes, so out of that N square, we have taken N kBT out. So what remains is N here. Now, if B dash N was much less than 1 is missing, or what is B dash? 2 pi r0 whole cube by 3 into N by V is much less than 1. But what is this quantity? 2 pi r0 whatever. So I just remind you that r0 was diameter. Hence, in terms of the radius, one can write this as 2 pi by 3, 8 times radius cube, which is the same as saying 4 into 4 pi by 3 R0 cube here. A cube is missing. I'm sorry. There should be an R0 cube here. And then this is the volume of the particle. So this quantity, which quantity? B dash n. B dash n is essentially, so n is capital N by V. This quantity is 4 times the volume. So 4n volume of a gas particle divided by the total volume of the box, which means that the gas is relatively dilute, because you are summing up the entire volume of all the particles into 4 divided by volume of the box, and if that's less than 1, one can write 1 plus B dash n, or rather 1 minus B dash n equal to 1 plus B dash n, right? And that's exactly what we do here. We write P plus, so this remains B dash U0 n square, and on the right hand side, 1 plus B dash n has been written as 1 minus B dash, 1 upon 1 minus B dash n upon nkbt. And the next step, if you just write n to be capital N by V, and capital N being the total number of particles, you can already see that the equation is getting to be closer to the van der Waals equation of state, right? So on the right hand side of the equation, you have nkbt, and all that you need to do is, I'm now replacing all the small n's, which was n, capital N by capital V. That's all that I have done. So that's what I have done here, and that's what I have done here. So this V now I'm taking on the left hand side of the equation and multiplying. I'm just basically multiplying V, and if you put it inside the brackets, this V will disappear and you have B dash n, and here you have nkbt, and this is the number of moles into RT, if you like. So this you can write as n divided by Na into Na, and Na into Kb is R, right? So you have number of moles into RT, and now you have the form, if you like, P plus A by capital V whole square, V being the volume of the gas, where A is B dash. What was B dash? 4 times the volume of an atom, into U0, the energy of interaction of individual between pair of particles, the length at the energy scale, the minima, the energy at the minima of the potential is U0 into n square. And what was B? The capital B, it is n times B dash. What was B dash? 4 times the volume of a gas. Sorry, volume of the atom of a gas, volume of an atom of the gas, right? So B is 4 times, so capital B is n into 4 times the volume of a gas. B capital A here is 4 times the volume of a gas into energy between a pair. I mean, the minimum energy, the minimum of the energy between a pair, the energy scale of the problem, into n square, right? So this has, as you see, B has units of volume, this has energy, units of energy. Just to check, capital A has units of energy into volume, and then this term A by V square is energy by volume, because this itself has U0 into volume. So then A by V square has units of energy by volume, and that will match the dimensions of pressure. And what have we achieved? We have achieved to get, using statistical mechanics, using Z2, where Z2 we wrote it in terms of the average. So we have got, using statistical mechanics, the van der Waals equation of state. We could write down these van der Waals parameters, which were parameters previously, in units of the atomic size, in units of the interaction, U0 interaction, between the particles, the energy scale of the problem, and so on and so forth. So what did we have to do here? Just to summarize, we had to calculate the partition function. So we started with the potential, an expression with the potential, short range interaction, r to the power 6 if you like, and a repulsive potential. Then what we did is we had to calculate the partition function. That's what you do in every statistical mechanics problem, where the kinetic energy part was easy to calculate and it didn't depend upon the potential at all. And then what we aim to do is calculate the partition function due to the potential. So that was the focal point. And in the next step, what we did is write down the partition function which comes from the potential in terms of the mean energy of the system. Now, mean energy, so partition function is an abstract quantity. It's a 1 by z is the basically the normalization factor, but average energy of the system is something which you can relate with. That's something measurable. It's like the internal energy of the system, and that now since that's something which you can relate with. You basically say, okay, this internal energy of the system, I am going to write it as half into n minus 1, which is the average energy of any pair of particles. That was the mean field approximation. Every pair of particles are interacting with u bar. And thereafter, what we did is basically rewrite. So basically, you had this term u average, and Z2 we broke it down. So basically what we did is this partition function contributing from U, we broke it down into in terms of Z2 pair partition function coming from a pair of interaction, and we did some more algebra so that we could write log of the partition function, where we had done suitable approximation in terms of the virial. Then we discussed the virial, played around a bit, and got the van der Waals equation of state. Now, I hope that you have come across van der Waals equation of state in previous classes. If not, we'll discuss it in class and have a separate lecture. But typically, van der Waals equation, even from the thermodynamic perspective or the kinetic energy or kinetic theory of gases, they already discuss it, the gas liquid. If not, I'll put a different lecture. With that, let me